Hi everyone, we are doing the project about improving the drawing. Given a set of data, which are sample from a curve, we hope to improve the drawing and increase the smoothness. We first consider the regression. Recall the meaning of regression. It investigates the relationship between dependent and independent variable. The line we get from the regression doesn't guarantee to pass through all the points, so regression will fail if the drawer wants to draw a slightly curled line. We next consider interpolation. Given a set of data, interpolation will find a function f of x that passes through a set of points. The given points are the data obtained from measurements. We hope to construct continuous functions based on these measurement discrete data. The goal is to find a linear combination of no functions to fit a set of data that impose n constraints. Furthermore, the solution is guaranteed and unique. Given a set of measurement from the function f of x, we have x0, y0, x1, e1, and up to xn, yn. The points x0, x1 to xn are called interpolation points. The polynomial Pn of x is called the interpolating polynomial of the data. If the interpolation points x0, y0, x1, e1, and up to xn, yn are distinct, then the process of finding a polynomial that passes through the data is equivalent to solving a system of linear equations, mathematical italic capital A x equals to b. Furthermore, it has a unique solution. Before proving the existence and uniqueness of the interpolating polynomial, we want first introduce Lagrange interpolation. Lagrange interpolation assume the polynomial Pn has degree n-1. Suppose we have n measurement data. We first define the interpolation function Pn of x as the summation of y and Li of x, where index I is from 1 to n. Each measurement data with index I has a corresponding polynomial Lk of x. The numerator of the Lk of x is the multiple of x minus interpolation points. The denominator of the Lk of x is the multiple of x I minus other interpolation points. There are some properties for Lk of x. When x is xk, Lk of xk is 1. On the other hand, if x is not xk, then Lk of x is not 0. The detail is shown in the following. Lk becomes 1 when we plug in xk. 1 multiply yk is yk. Therefore, we can guarantee the approximate polynomial, Pn, will pass through approximate point xk, yk. The degree for the polynomial should be no more than n-1. Yi are constant and the numerator of Li polynomial has degree n-1. Again, the denominator of Li is constant. Therefore, all Li polynomial has degree n-1. The summation of the polynomial of the same degree should be equal or less than. Therefore, Pn has equal or less than n-1 degree. Next, we want to introduce the main theorem of polynomial interpolation to ensure the interpolation we have is unique and exist. Suppose we have n measurement points with distinct xi. There exists on and only one polynomial p of degree n-1 or less that satisfies p of x I equal to yi with index from 1 to n. We hope to prove by contradiction. Suppose the interpolation is not unique. There exists another solution, called q of x. Q of x also has degree at most n-1, and interpolate all points also, by the design of the Lagrange interpolation. Therefore, we have p of x1 equal to q of x1, p of x2 equals to q of x2, and etc. Define h of x to be the difference of p of x and q of x. Apparently, there are indistinct zeros, since p of x1 is the same as q of x1, etc. By fundamental theorem of algebra, a degree d polynomial can have at most d zeros, unless it is identically zero. Therefore, H is the identical zero polynomial and P is equivalent to Q. Therefore, P of X is the unique solution. Now we have the function to approximate the curve. We will need error function to know how accurate our function is. The starting point is straightforward. The error is defined to be the difference between the actual value and the estimation value. Therefore, we have f of x minus p of x. The vertical distance between f of x and p of x is the error. Suppose our original function f of x is n plus 1 times continuously differentiable on the close interval a and b. The interpolation data are n plus 1 distinct numbers in a and b. Pn of x be the interpolating polynomial of degree almost n that interpolates f of x in a and b. The proof is trivial if the input, x bar, is one of the interpolation data, since the value of f and p are the same. Suppose the input, x bar, is not one of the interpolation data. Suppose t is another point in the close interval a and b. The error function the difference of the error at t and the error at x bar. By generalized Rolle's theorem, there exists a point, C, in close interval a and b. This is the formula for Rolle's theorem. Let x is equal to xk. Suppose we have a 3-degree polynomial. The first time we differentiate the polynomial, we will have the leading coefficient multiply 3. We differentiate the polynomial again, and the leading coefficient will be 3 multiply 2. If we differentiate the polynomial again, we will have 3 factorial multiply the leading coefficient. Here, we consider t minus x0 multiply t minus x1 and up to t minus xn. The leading coefficient of this polynomial is 1 with degree n. So when we differentiate it n plus 1 times, we will have n plus 1 factorial. Consider the formula Lk of x. When we plug in a value x bar, the denominator becomes a constant. When we differentiate Lk of x n plus 1 times, we can take out the denominator directly, and differentiate the numerator. So we obtain n plus 1 factorial over the original denominator where x is replaced by x bar. And then we get the result. Here is the snapshot for our application. The measurement data is labeled as x. We use the library from MATLAB and plot the graph. So this is our project. Have a wonderful day.